In 2017, the seminal paper, Attention is All You Need, introduced transformer architectures to the world of artificial intelligence and machine learning, and it pretty much changed the game for the way neural networks are implemented in a lot of cases. They're used for translation, natural language processing, images, and even video now, and famous implementations like GPT-3, Dall-e, Imagen, etc. use transformers as a basic element of what they're doing. Even more importantly, for Tesla fans, Andrej Karpathy said that Tesla uses GPT-like transformer architecture for their full self-driving beta. But of course, this begs the question, what the heck are transformers? How do they work? What are their advantages? And why is it such a big deal for the Tesla AI team? Let's take a look. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Hey y'all, it's Dr. Know-It-All. So first of all, I want to have a couple of admissions here. Number one, this video is partially selfish because I need to use transformers in a research project that I'm working on. So I needed to really bone up on transformers and I didn't have it down very well. So I've spent the last week really digging deep and trying to understand transformers. And of course, a friend of mine, Scott Walter, actually, who's been on this show several times recently, told me if I want to prove that I know something, I should try teaching it to other people. So I thought, well, here we go. I'm going to try to teach transformers to all of you. I'm going to start off with a pretty high level overview with a lot of hand waving and stuff. Then I'm going to get into more of the mathematics of it and everything. I'm never going to actually look at code or even pseudocode, but I'm going to look at the math behind transformers. And then at the end, I'm going to talk about how Tesla full self-driving benefits from transformers and why it puts Tesla so far in the lead in terms of full self-driving. So if you're not really into math or anything like that, of course, you can look at the chapters and just skip the section on how transformers work. If you really do want to understand the math behind it and how all of this stuff works, I will do my best to explain it in that section. So anyway, I had to do a ton of learning to get boned up on this topic, and I'm actually a little bit afraid to present it to you all because it's a pretty deep and complicated topic. So hopefully I do pretty well, and be gentle in the comments if I make any small mistakes, hopefully small mistakes. All right, so let's do a little bit of an overview first. What are transformers and why are they useful in general and for Tesla full self-driving in particular? We got to start with the fact that convolutional neural networks, CNNs, are great, and they've done great since 2012 when AlexNet destroyed the ImageNet competition and launched CNNs into the forefront. So they do really, really well, but they have a couple of big problems. Number one, they are local first, which means that due to the convolutional nature of it, they only look in their own really close neighborhood in a picture or something like that, in general at first, and then they spread out over time. And the second problem is that they really don't have any memory. So if you think about like a video frame sequence or something like that, you could run a CNN on one frame and then on the next frame you run it again. It has no idea what happened on the previous frame. So that lack of memory is a pretty big deal. To try to deal with the lack of memory, particularly in natural language processing issues, RNNs or recurrent neural networks and LSTMs, long short-term memory networks, and other networks also, were extensions of CNNs and kind of modifications to the architecture to try to provide memory. But the memory really doesn't help the local issue with these architectures, and also the memory is very limited. There's kind of like a little window you can slide back and forth. Anyway, if you have an interest in learning more about CNNs, just check out the link to my video that I did. I did a pretty in-depth dive into CNNs themselves. So transformers. Transformers are new as of 2017. They're a deep neural network architecture. They transform dimensions, I guess might be a way to think about this. You could think about it from going from the time domain to more of a frequency domain or something like that, like Fourier analysis, or an even better and more simple to understand conversion might be from Cartesian coordinates to polar coordinates. So Cartesian coordinates are like the XY coordinates of something, right, of a graph or whatever that you're used to from high school mathematics and geometry and such. Polar coordinates, on the other hand, are something like this, where you're seeing like how far around a circle and how far away you are. So something like a watch. A watch is a really good example here. So this is a mechanical watch, obviously. And the second hand, if you try to describe the second hand in Cartesian coordinates, it's going to be an utter nightmare to try to figure out the equations to tell how this thing is moving around in time. Whereas if you convert this to polar coordinates, all you're saying is it's going 2 pi divided by 60 radians per second, and the radius is whatever this distance is that you measure. I don't know what that is. A centimeter or so, something along those lines. So anyway, this is really, really simple. It's very, very easy to describe the motion of a second hand on a watch using polar coordinates rather than Cartesian coordinates. So transforming things is kind of in the nature of what a transformer does. It's not doing Cartesian to polar coordinates, but that's just kind of an analogy for you to understand. But basically, it's transforming things. It's taking away the sort of sequential nature of stuff. And that's one of the most important aspects, because what it does is it allows it to be less temporally and spatially localized. So transformers were designed for natural language processing. In other words, auto-completion of sentences, translation, chatbots, text generators, etc. And GPT-2 and GPT-3 are prime examples of transformers. In fact, they happen to be called generative pre-trained transformers. So transformers is right in the name. Later in 2020, they were recast to be able to work on images, and I'm going to talk about that, and later even on video sequences as well. I'm not going to go too deep into video sequences today, even though they're really, really crucial to Tesla's full self-driving. It's just another extension of what we're already going to be talking about with the image-based transformer. So in order to keep this video reasonably short and focused, I'm just going to kind of hand wave about that. But you can definitely look at papers and videos on that topic as well if you're interested. So as per the name of the original paper, they use attention as the key element in their work. In other words, what they do is they look at words or images or video, and they determine what other words or what other pixels or pixels in a video frame sequence deserve attention. And FYI, RNNs and LSTMs can and have had attention added, but transformers prove that attention is all you need, which is thus the title of the original paper. In other words, you can chuck all the complex machinery of these other architectures and just focus on attention. And just as a quick aside here, the word attention is very important. It's sort of like focus. I guess that might be a different way to put it. It's like, where are you paying attention to things, right? So it's not like standing at attention like a military person. It really means like, where are you looking? So you could think of it as focus, but paying attention is probably a better way of putting it. I just want to make sure that people understand that. So we're not talking about like people in the military standing at attention. We're talking about where is this thing looking in a sentence or an image or a video sequence. All right, so that's the real basic elements of a transformer. What are its advantages? Number one, it can pay attention to anything and at a very flat level. It doesn't have to have depth in order to pay attention to things. In other words, it can pay attention to any nearby words, any other pixels in an image, any other pixels in a frame of video, etc. This is a huge advantage over CNNs for vision work, as CNNs primarily pay attention to things in the neighborhood of the current pixel, as I said. So what they do is they start by looking at things that are really, really close to each other, and then as you go deeper and deeper into the layers, it can look further and further away. Transformers sort of short circuit this by being able to look all around themselves at the same time from the beginning. Also, transformers are architecturally simpler than LSTMs, although they're still pretty complex, as we're going to find out. And crucially, they have less memory loss. In fact, theoretically, they have zero memory loss, but that's not practical with the size computers and things like that. But anyway, they can pay attention to whatever they want for as long as they want, and that's also really important. An RNN, for example, has to remember important elements through many sequences of time. You can think of it temporally like each word is a time step, and it has to remember back to these other time steps through all of the other pieces of the RNN. In other words, recurrent, so it's going backwards, right? So if you have two words that are separated by 7 or 8 words, it's going to start to forget about that because a lot of gradients and other things are going to get messed around with, and it will have a hard time like remembering earlier words in a sentence. But as transformers can pay attention to kind of anything, the transformer can go like, oh, I really need to pay attention to this first word in the sentence, even though I'm 7 words later in the sentence down the line. Also, very crucially, they are non non-sequential. In other words, you can read in everything you need to know and read out what you want to know. In other words, you can input a sentence as input for a translator rather than one word at a time. And the effect of this is not just that it makes it better at remembering things, but it also becomes highly parallelizable. In other words, it's totally different from RNNs and LSTMs that are by nature sequential, so you have to feed things in one at a time and read things out one at a time. Transformers, on the other hand, can be run in parallel, which means that they are fantastic with GPUs, TPUs, neural engines, etc., as the calculations can be split amongst many, many threads at the same time. So this makes them much, much more efficient than RNNs and LSTMs. On a more theoretical basis, they're also more general than CNNs, RNNs, LSTMs, etc. They can learn just about anything better than those older neural network models. And also, very importantly, and think about Tesla for this too, more data leads to better performance without much drop off. So RNNs, LSTMs, CNNs, etc., they learn really, really well as you get a bigger data set, but eventually they just kind of top off. So if you have 10 million images or something like that you're feeding it, it does better, and 20 million it does better, but eventually it just rounds off. And when you get up to like 50 million images, adding another 10 million doesn't really help that much. LSTMs, on the other hand, can continue learning for as big a data sets as we have right now. So that's actually huge. And this leads us to the disadvantages of a transformer. The first disadvantage is handled fairly easily. That is, the elements of a transformer really don't know where they are in space or time. And this is the reason they can be computed in parallel. In other words, you read in an entire sentence at once, but it really doesn't understand where things are in space, right? It doesn't understand the ordering of the words. So what you have to do is you have to compensate for that by embedding position into the vector that represents these words. And that does add some complexity to things, but it's not that big a deal. The much, much bigger problem is that you need tons and tons and tons of data. And again, think about Tesla. We're going to get to that later on. But you might need 100+ million data points at least just to match the performance of some of these other architectures like LSTMs. But as you get to 150 and 200 and 300 million and a billion data points, then these things really take off. And transformers go from being sort of adequate and approximately the same as CNNs, RNNs, LSTMs to being much, much, much better. And the more data you throw at it, the better they get. So it's a really big disadvantage if you don't have access to a ton of data, but hint, hint, if you happen to have access to lots and lots and lots of data, then transformers are definitely the way to go. All right, so time to get super geeky. You can skip this section if you're not interested in the math, but I'm going to talk now about how transformers work. We're going to get into matrix multiplication, KQV, alignment of vectors, multi-headed attention, softmax, probabilities, word and image embedding into vector space, and positional encoding. What we won't cover here, as I said before, is any of the coding itself. TensorFlow with Keras and PyTorch are the primary APIs that people use these days to do this stuff, and I've personally been researching TensorFlow with Keras. And of course, there's lots of coding examples online if you want to go learn more about this with specific examples. But I felt like for this particular presentation, the math was more important than the code. So I'm sticking to the math. So we're going to start here with word-based transformers, which was the original 2017 Attention is All You Need paper. This image right here is kind of the primary thing. Well, this and this one. So there's two images that we're really going to focus on from this paper. The main concepts we're going to learn about here are word vector embedding, positional embedding, self-attention matrix, masked attention matrix, multi-headed attention, word embedding, KQV or query key value, and along with that, dot products in spades, tunable parameters, vector alignment, and probabilities and softmax. So let's start with word vector embedding. Words are not understandable by a computer, so what you have to do is turn them into numbers, and essentially that means turning them into a vector. And if you don't know what a vector is basically a magnitude and a direction. So here you can see this red vector V. The best way to think about this might be like speed versus velocity. So you could say I'm going 100 kilometers an hour. That's the speed, that's a scalar number. It doesn't give you a sense of direction. But if you say I'm going 100 kilometers an hour northeast, that means that you're going in kind of this direction-ish, right? So you're going that speed, but you also have a direction. And the other really important thing about vectors, as you can see here, is that you can decompose them. So basically, I can decompose the x coordinate of this vector and I can decompose the y coordinate of this vector. So it'd be 7 in this direction and 1, 2, 3, 4, 5, 6 in this direction. So it's 7 in x and 6 in y, and you can actually make that into a vector and represent that vector as an xy pair, at least if it was coming from the origin. Here you'd have to subtract the beginning and the end of it, but anyway, that gets more complicated. But anyway, a word vector might not be quite as obvious, but what you can do is you can take a 10,000 word dictionary, for example, like, right, you've got definitions of 10,000 English words or something. And what you can do is turn that into a 10,000 unit vector, right? So it's 1 by 10,000, and you make this a binary vector. So every single one, except for the word you're interested in, which you just give it a spot. So you can just do it alphabetically, right? So the word aardvark or something might come early in the alphabet. So it's got a very, very early number. And so let's say it was the first word in the alphabet, actually A would be that. So I'll call it number 2. So anyway, you have 0, and then you have 1, and then you have 0, 0, 0, 0, 0 for 9,998 more zeros. So it's called one-hot encoding, which basically means that the position of that vector represents what the word means. So the computer can learn that the word aardvark is this vector, right? A bunch of zeros with 1 in the second position. So that's how it kind of learns what a word is. I know that doesn't make sense to us human beings, but that's how computers like to work. So we basically get a 1 by 10,000 vector for every single word in the dictionary. And then we get to position embedding. Like I said, transformers don't understand where other words are in a sentence. They sort of read everything in at once. So what you have to do is provide it some hints. And there's lots of ways to do this, but we're just going to do it via counting today. So the position embedding can just be 1, 2, 3, 4, 5, right? You just count the words, and that's the position embedding that you have. And essentially what you do is you add these two vectors together. You add the position and the one-hot encoded vector. You have to kind of adjust the dimensionality of it and all that kind of stuff to make it all work. But basically the one piece of the puzzle is telling you where in the sentence this word is, and the other piece of the puzzle is telling you what this word is and what it means, essentially, to the computer, of course. So of course the computer doesn't know what the hell the word aardvark actually means. It only understands that this thing with a number 1 here is what human beings will eventually come to see when it gets translated back out to human language as the word aardvark. So this is why if you think about these computers becoming conscious and stuff, as in some people from Google recently, it's probably unlikely that they're conscious at this point using this architecture. They really don't understand things. They just have a really good knack at translating between them or finding the next word or whatever it is you're looking for. And then we get to the self-attention matrix. This is a matrix that has tunable parameters that specify what each element is looking at or paying attention to. And tunable means that the numbers in the matrix are trained to get better. This is what happens when these neural networks are being trained. This is the crux of the way that transformers work, of course, and all neural networks. They change these numbers around to improve the output and do a better job. So each word can pay attention to itself and to the words in the sentence. And the matrix shows these values numerically. I'm going to get to a specific example here in just a second. But anyway, after normalizing and softmax, which I'll talk about a little bit later on, each row and column adds to 1. And after training, these probabilities will be used to specify which words the current word attends to or focuses on. So let's look at this situation where we want to translate "the dog barked" to "le chien a aboyé." And I hope aboyer is the word for bark. I'm not positive about that, but I think that's correct. Anyway, so we've got a start token, which just basically says, hey, I'm starting here. We've got an end token. You can see that on both of the ends of these things. And you could imagine what's happening here. These are made up numbers, by the way. This has nothing to do with real training. I just made up a bunch of numbers that would work in this situation as an example, just FYI. But anyway, what you do is you read in this sentence, "the dog barked," and then you provide the positional information, right? So, 0, 1, 2, 3, 4. And then what happens is over time, these numbers get trained. And so you can see that each word is paying more attention to itself than anything else, but it can also pay attention to other things. And then of course you do the same thing with your output matrix, which is your translated thing. Note that you don't have to have the same number of words. We've only got 3 words in the English sentence and we've got 4 words in the French sentence. So you can adjust these things. These are called sequence to sequence and they don't have to match each other. And while we're at this, let's talk about masked attention matrices. These are very, very important to training. Not so much for the deployment models, which would be where you're actually using them out in the world, but as you train, what what you do is you take any future word and you make that negative infinity. And notice what this does. You get le, which has, its own self-attention, but then it has no idea, because these other values are negative infinity. It doesn't know anything about the future. And this is the super important part, because what it has to do is learn to train on what it already knows to predict the future, right? So it's trying to predict the word dog, le chien, right? So it's trying to do that, but if you gave it the word dog already, it would already know. So that would be cheating, right? So essentially you're inputting the dog barked in English, and then you're saying le, you're saying, hey, here's the word the. What's the next word in French that I need? And that's the important part. It doesn't have access to this word, and it also doesn't have access to any other words in the sentence after that. So it has to be able to predict what the word is in the future. So masked attention is used in the output stage of things, and the input stage, you know all of the information, so you have all of this. The output stage is what you're learning, and so you're sort of tuning all these parameters to make it very predictable that when you get the word le, the next word translated from the dog barked is le chien. And if you go back here, you can see we've got our input embedding, right, which was the word vector and also the position vector added together, concatenated. We get this positional encoding. We then put it through this multi-headed attention, which is that thing that I was just showing you. That would be that breakdown, that matrix. And then as we go to the output, which is kind of the predictive stage, we're looking at this masked multi-headed attention. So you can think of this as the English sentence saying, the dog barked. And then the masked multi-headed attention is saying, what is this going to be in French? So you're tuning this entire network to translate English to French. And so what it's doing is it's asking that question here, and it's got to be masked. Then after that section, we actually will do another multi-headed attention, and we can keep going forward. And by the way, notice that this says n times nx. You can have as many multi-headed attention layers as you want in each of these, in the input and the output. And at the end of all of this stuff, you get a probability. So remember, we've got 10,000 words in French too, or whatever it is. But the idea is that we're looking for the word chien in there. So wherever that is, whichever one hot vector in the French dictionary it is, that's what it's looking for. So the probability distribution should be 10,000, approximately 0, and one that spikes up is close to 1. So that's what we're looking for. So we take that, we translate that to French via a lookup table, and we pop out the word chien. And then the multi-headed attention part means that there are many, many attention matrices that you're using. This example just shows 2, but what you get is generally, I think 4 is kind of the common number to use. But basically, you don't just use one of these attention things, you do a bunch of them, you initialize them randomly with random numbers. They all learn separately. And then in this step where it says add and normalize, you're aggregating these multi-heads together. So if you have 4 of these, they all sort of average out. So, 0.2, 0.3, 0.1, and 0.5 or something, whatever that averages to. You add them up, divide by 4, and that's what you get. So it's kind of a voting system. And the importance of this is just like CNNs, you don't just want one filter, you want many, many filters so you can get more robust performance. Here, what you're getting is more robust performance. You don't get a single attention head that just dominates things completely and goes way off track. So then we get to what does attention actually mean? And this is where things get really interesting. So here we've got what we call QKV. Q is the query, K is the key, V is the value. The best way to think about this is K and V are kind of attached to each other. So the key, for example, again, in a dictionary, you would look up the word aardvark, for example, and it's kind of weird that I picked aardvark, but anyway, I don't know. It's a standout kind of word. What are you going to say? So aardvark is the key, and then the definition of the term aardvark is the value. And by the way, the definition is a nocturnal burrowing animal with long ears, a tubular snout, and a long extensible tongue feeding on ants and termites. So that's the value. You've got the key aardvark, you've got the value, that definition, and then the query might be, somebody might do a Google search and they might say, what is an aardvark, or definition of aardvark? And then what you do is you use that query to go seek out the correct key to find the web page in this case with the proper value. And note that this is all probabilities. There is no absolute best web page to go search for what an aardvark is. There's just something that Google is going to have determined is approximately ultimately the best page. So it's going to have the highest probability, and that's the page that Google is going to serve you. So here in the case of transformers, you can see how this is actually being implemented. What you do is you take the query and you dot product it with the key. So that's the matrix multiplication here. And what that gives you is the overlap between the two vectors. So here, capital Q and capital K are matrices. They're like multidimensional matrices. But while doing these calculations, you can break it down into vectors and think about it that way. And essentially what you're doing, this is the dot product here, is you're taking the overlap between these two vectors. So vectors A and B, the more highly overlapped they are, and if you've ever used cosine before, you're going to understand this right away, that basically when the angle goes to 0, the cosine goes to 1. So that means they're fully overlapped with each other. So the two vectors are pointing in just the right direction. And that means that they're highly correlated. On the other hand, if the A and B vectors are at like 90 degrees to each other, that means that they have little to no relationship with each other. So that means you can throw away most of the words that you're looking for are going to have 90-degree angles between the two vectors, the Q and the K vector. So that means they're going to produce zeros. But a couple of these, and hopefully the word aardvark in this case, is going to have the Q and the K vector are going to be very highly aligned with each other, so it'll produce a very high probability. And then what you do is you scale this, you have to renormalize it a little bit. You can add the optional mask if you're searching for the next word, right, which is the negative infinities. And then you do a softmax, which I'm going to talk about in a little bit, and out pops probabilities. You then take that vector or matrix, depending on which thing you're looking at, and you multiply that times the value. And that pops out the predicted next word or the predicted classification in the case of an image-based version of this. So you can see here we've got two dot products per one of these multi-head attention things. The Q and the K are dot producted together, and then the result of all of this stuff times the V, or dot product with the V, is done. So when Elon Musk talked about everything is always dot products, which is just multiply and add over and over again, and if you haven't seen it, definitely check out my video on that topic as well. I go into this in more detail, but basically there is a ton of this stuff going on. Multiply, add, multiply, add, multiply, add. So it's a lot of things going on. And again, the more parallelized you can do this, the more you can put it out on a GPU and have all of the threads running at once. So the better off you're going to be and the faster this is all going to work. But anyway, when we get done with all of this stuff, what we output is some sort of probability. We then throw it back into this network and we do some other stuff, linear, dense layers, softmax, things like that. And out pops a single prediction for the next word in our translated sentence or whatever situation it is. And if you care, this is literally how this whole thing works. Attention of QKV is the softmax of QK to the T divided by the square root of the dimension of K, which would also be the dimension of Q as well. But basically it just keeps the numbers relatively small by dividing them. It's not quite normalizing, but sort of like that. And then you dot product that with the matrix V. So when people say attention is all you need, you can say, oh, softmax of QK to the T over root DKV is all you need, right? And we should probably, oh gosh, I should make a shirt like that. That would be really, really funny. So maybe I'll do that. Check out the merch store. I might actually do that. That would be pretty darn funny. But anyway, mathematically, that's what they mean by attention. It's a very specific thing. And then let's turn to probabilities and softmax. You see it explicitly here, but it's actually used in other places inside, because you can see here that softmax is also used in our attention layers as well. So softmax is all over the place. The important thing to understand is that probabilities are key for anything with neural networks. They're always looking for the most probable thing. And what that probability means is something out of 1. So what you're looking for is a number between 0 and 1 that's as close to 1 as possible. That's your maximum probability. And the entire vector, all of the things, if you have 10,000 units or something in a vector, all of those 10,000 elements have to add to 1. So if one of these things is 0.9, then the other ones all have to be tiny little numbers so that it never exceeds 1. And here you can see in my completely trumped up numbers, right? I've got everything adds to 1. So it's 0.9 and 0.1, 0.85 and 0.05 and 0.1, right? So I just made them all add up to 1. But by using softmax, you're guaranteed to get that. And the formula for softmax is this. Essentially what it does is it creates more of a contrast. So smaller numbers get depressed and bigger numbers get raised. And then by dividing by the sum of e to the zj, it actually forces everything to add up to 1 in the end. And so when you get done with softmax, The goal is to have a whole bunch of very, very small values in your vector or your matrix and have one or two that's relatively high. And that's the probable outcome that you're looking for. So once again, let's take a look at this entire thing from the attention is all you need paper. You're going to have your inputs, which in this case would be our English sentence. You embed them, you add positional encoding, you do multi-head attention, you add and normalize, you do all of that kind of stuff. Multi-head attention being this guy again. And then what you do is you take your output sentence, and so you've got your French words in this particular case. You do the exact same thing, positional encoding, output embedding. Then what you do is you use masked multi-head attention. So it's got those negative infinities for the future, so it can't see the future. And then after that, you add in the information from your input sentence, do another multi-head attention layer, feed forward, dense layers, softmax, output probabilities. The probability will be the next word or words in the sentence or something in this particular case. And that's all there is to it. That's all that's in a transformer. But wait, we can actually do images as well. So what are image-based transformers as opposed to language-based transformers? This all started in 2020 with a picture is worth 16 by 16 words, and an image-based transformer actually uses images as input as opposed to words. So of course the obvious thing is to think, well, obviously what you're going to do is just input each pixel as an input into the transformer, and then you can pop out a classification or whatever it is that you're interested in. The problem with this is that the input space is way, way, way too large, and it gets way out of control. So if you think about a sentence might have 10 words in it, right? So it has 10 inputs and approximately 10 outputs. But a tiny, tiny little image, it's 256 by 256 pixels, which is like postage stamp size, has 65,536 inputs. So you just can't handle that. It's just too big. So for a while, for a whole couple of years, people thought that images were just going to have to continue with CNNs and potentially RNNs and things like that. But then the pictures where 16 by 16 words came out, and the basic insight here is this little thing right here. You take your image and you break it apart into patches. And these patches just so happen to be 16 by 16 pixels, which is why the title of the paper is A Picture is Worth 16 by 16 Words. So the additional concepts that we're going to touch on here are what are image patches, spatial embedding, classification vector, which by the way is a vector that contains all of the classes we care about for something like a classification problem. So right, if you're looking for dogs versus cats or something, that would be 2 whole classes. But we could say 1,000 classes if we want to have a bunch of stuff, or 10,000 classes, whatever it is. But anyway, we'll have a vector that contains, again, one hot encoding, right? So a dog in a 2 case, right? If it's a dog or a cat, you'd have a 1 for a dog in the first place and a 0 for cat. And then you flip it and you have a 0 for dog and 1 for cat. Same thing, you just have multiple thousands of those as opposed to just 2. And then the masking that we talk about in the sentence structure can actually be done with patches instead. So you can mask out future patches. So it has to predict things and it has to come to understand what they are. All right, so patches are actually probably easier to understand than the whole word thing. So again, what you can do here is you can divide the image up into patches. In this case, we've got 9 patches, right? 3 by 3, it's a tic-tac-toe board. And each of those patches is 16 by 16 pixels big. So if instead we had a 256 by 256 thing and we divided it by 16, we would only have 16 inputs, because 16 times 16 is 256. 16 inputs is more like a sentence, right? You can deal with 16 inputs. That's a small amount, not like 65,000 plus inputs. And then what you do is you take each one of these patches and you unroll it into a vector, right? So each particular pixel, just go pixel, 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 unroll it all out, and that becomes a really long vector that represents that entire patch. And if we look here, you can see I kind of mocked up something like this really, really horribly composed image. I used this picture on purpose. It's a very badly composed image, but what you can see is I've gridded the whole thing up into equal sized patches. And then each one of these patches, like patch 1 up here, would be unrolled into its own vector. So you'll end up with 20 by 16 patches in this case, and each patch is going to be however many pixels that is, right? So this would be the mocked up case that we're dealing with. And then we need to deal with spatial embedding. And as that turns out, that's actually really, really easy. You basically just count. So you start in the top left corner, you count that as patch 1, patch 2, patch 3, go to patch 20, go back down here, patch 21, and just keep counting up until you get to the end, which is patch number 320 in this case. So anyway, this is the way you would do it. You just patch everything out and then you spatially embed it. So remember, there's the word embedding that told the network, the transformer network, where these things were in time. with the words. Here we have, where are we in space? Well, that's embedded just simply via these numbers. And so it basically learns to understand that the number 1 for spatial embedding is located at the top left. You don't tell it that explicitly, but it learns that as part of the training process. And then the really wild thing after this is you can basically just feed all of this stuff into the previous transformer architecture, and it will pop out some sort of answer. But here what we're looking for is prediction of a classification rather than the next word. So we're going to pull all of these things out, and at the end we're going to take this C0 here, which is a little extra thing that we've added. Like I said, it's the classification vector, which has all the different possible classes, and that's the thing that we care about. So at the end we'll pull all this stuff out, and we'll end up with a prediction that this is going to be a dog, or in this case it's a person in this image, and that will be the classification for that image. And again, this uses KQV, it uses softmax, it uses probabilities, all the same stuff that we learned about before. But crucially, we can also do this for pieces of these images. So for example, I could take this section over here, and I could divide that up, and I could say like, oh, this part over here is a car. So I could classify that part of the image as a car, and I could classify this part of the image here as person. And perhaps I can do gesture recognition. It could say like, oh, this person is shrugging. This was from our flat tire episode, by the way. And if you haven't seen that, you can check that out as well. But anyway, so you can classify different parts of the image as different things. Of course, you can classify the bottom part down here as like grass or something like that. So right, and telephone pole and all of that kind of stuff. So really, really crucially, it's not just entire pictures, but you can classify the whole thing. And what you can therefore do is segment this thing out and understand what they are, or do semantic segmentation. And by the way, I've done a video on that as well. So you can go down a whole rabbit hole of my videos, just watching this one and then following up with all the other ones. But anyway, this allows you to understand a scene and all of the pieces of that scene. And it allows you to relate one part of a scene to another. Like I said, this is a bad picture, horribly composed. But basically, if somebody's query was, what is John shrugging about? If you were doing a convolutional neural network, it wouldn't understand because it wouldn't be able to see anything past where I am. But by using a transformer, it could go like, oh, I should pay attention, like all of these pixels over here, the John shrugging pixels, should pay attention to this part over here, which is the Tesla on a tow truck pixels. So that kind of thing would give you the information that you need to understand to know semantically what is going on in this scene. And that's where transformers can really shine. And of course, you can break this up and you can do all of these operations simultaneously, which means it's really, really good on a GPU or potentially full self-driving hardware. All right, so that's vision transformers. What about video-based transformers? As I said, I'm not going to go too deeply in this because this is already super long anyway, but basically what you can do is sequential patches in addition to spatial patches. So you can look at patches over time as well as just across an image. And of course, you have to add temporal embedding as well, which means basically you say frame 1, frame 2, frame 3, etc. So you have to do that. And essentially what happens is this extends the visual transformer by adding a time dimension, in other words, multiple frames. But that means that it can not only pay attention to things that are far away from each other in an image, but far away from each other in time. And that is the crucial element here, which means that it has a temporal memory. And that part is really important. And of course, if you want to know more about this, you can just look up some videos on YouTube or read some papers or things like that. There's tons of stuff out there on this. All right, so if you've stuck with me this long or you just skipped ahead to this part, let's look at why do transformers transform Tesla's full self-driving beta. I kind of like that. So just to be clear, I don't know anything internally with Tesla. I'm just looking at this from the outside, don't work for them, don't have, inside information. So these are just guesses on my part. And also I want to be really, really clear here. There's two pieces of this puzzle. One of them is training. So that would be these massive supercomputers like Dojo and things like that that are implementing these things and training, and they need a ton of resources. The other part of this is edge computing, which would be hardware 3 or eventually hardware 4, which is only used to infer the answers from this. So as opposed to all of this training, they just run through the whole thing once and they get an answer. So they're just doing deployment or inference, and that doesn't take nearly as many compute resources. But what are our advantages here? Well, number one, highly parallel, right? So instead of running things sequentially, which is going to take a long time, you can run entire images and image sequences simultaneously through multi-threading on neural engines or GPUs. And that, of course, leads to a better frame rate, faster predictions, all of that kind of stuff for Tesla Tesla's full self-driving. You of course can also look at disparate parts of an image or an image sequence, and you could determine associations that are important. Again, why is John shrugging? Because of the car being on the tow truck, right? Those are the kinds of things that you can associate that are really difficult to do with traditional CNNs. You can do that much more easily with transformers. A realistic example might be that you see one deer on one side of the road and one on the other side of the road, and the computer needs to understand that those two things, while they're on opposite sides of the image, they could interact with each other like, oh, two deer, and that deer, one of them might run out into the road to go join the other one. So by associating the two deer and realizing that they might have a relationship with each other, it might be able to understand more rapidly that a deer might run into the road and slow down prior to other methodologies. And then of course, even more usefully, the video version of this can look at many frames and determine what's important across all of those frames. And of course, this is super helpful for things like obscured objects like people or something like that go behind other objects, or vehicles that go behind other objects. You need to be able to keep track of all of this stuff. And that's something that transformers really shine at. And of course, transformers can remember for arbitrarily long periods of time, as opposed to RNNs, LSTMs, etc. So at a stoplight, for example, you need to remember that there's a car on the other side of a truck or a person being hidden by that truck. And you might need to remember this for 30 to 60 seconds or something while you're waiting for that light to change. And if you use something like an RNN, you're going to have a time window after which it's just going to fade out of memory. It just won't remember anymore. Too many multiplications, too many things like that, it's going to forget about that. So that is a bad thing. Which is why I know that Tesla, at least at one point, had implemented two RNNs, a spatial and a temporal RNN, so they could remember in two domains. I have a feeling with these transformers that they're probably able to scrap that and just go with one single architecture for that. And that's going to be a really big advantage. So transformers being able to remember better than these other architectures is absolutely huge. And finally, we get the advantage that performance continuously improves with more and more data. CNNs, RNNs, etc. level off and they can't improve with bigger data sets, but transformers can use all the yummy Tesla full self-driving beta data. And this, in my opinion, is the biggest reason why Tesla's full self-driving lead is really unassailable. If transformers are the correct answer for full self-driving, and it looks like they are, then you just can't solve it better than Tesla without more data than Tesla. And Tesla is far in the lead with data. So this is all amazing, and it's really looking good for Tesla's full self-driving. All right, I hope you enjoyed this super long and detailed episode. If you did, please do like it so other people can find it. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon. Thank you all so much for your support and your help. And actually, some of the folks actually helped with this episode itself, vetting the information that I was giving. So hopefully they did a good job. Anyway, if you want to join the team, definitely check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on. So check it out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.